And where this really took off deals with when you look at matter. So you take a big piece of iron and you stick it in the fire and you heat it up and you get really bright metal, shiny. But you do the same thing with metal particles distributed in the gas and you get something very different. Rather than this rainbow-like emission spectrum that we see for heated up metal, if you do atomic materials, elements that are distributed in the gas phase usually, you get a very different behavior. Rather than seeing a broad, diffuse spectrum, you see lines. These are what we call line emission spectrums. We see this actually what we call in like neon science and neon lights and even fluorescence. I took a couple pictures with my phone, and I'm just going to show them here. So we have a light that shows our standard rainbow-like pattern, but when you have a discrete material like a neon lamp, a fluorescent light, for instance, or a neon lamp, like this super cool cup that I occasionally drink from, it shows distinct lines rather than distinct narrow lines. And these are what we call our emission lines. In fact, each element has its own unique emissions spectrum. So we use spectroscopy to determine the spectrum of the compounds. And there was no easy way to describe why these lines were the way they were. Why was this thing emitting at only specific frequencies? Specific frequencies of light means specific energies of light. Because, again, the frequency is dependent on the energy. So why? Along came another chemist called Bohr, and again, he did what all chemists do, is he cheated. All right? He said, well, you know, these emissions are coming from the electrons of the atom. And so if we just pretend, like, again, this is back when we had our Rutherford model of the atom, the electrons on the outside and the protons and the neutrons are in this interior, borrowed this idea of quantized energy and said if photons can do it, electrons can do it, and locked the electrons into specific energy regions of the atom that we now call orbits, or orbitals. This is so his model, this planetary model, was that, well, the electrons orbit around the atom in discrete orbits. And the only way you could describe these changes is that they represent particular frequencies of light associated with changes from one orbit to another. So-called quantum leaps, a leap from one orbit to another. The hard part to conceptualize is that these are electrons that are existing in these orbitals. To go from one orbital to the other, it spontaneously moves from one to the other. It doesn't actually travel between those two spots. So it's able to go from distance A to distance B without going through the middle distances. Right? It's so-called quantum leap. It's able to leap from one energy level to the other without actually moving through the intervening space. Again, the laws break down. So by applying this quantum model, by applying this idea of quantized energy to the, what Bohr was able to do is, using this quantized model, was predict the energies of a electron orbiting the hydrogen atom. And so he just based the orbitals upon a number, n, which we're just going to call this the principal quantum number. And he said that this is an energy level of the electron. And so the lowest energy level would be n equal to 1. The lowest energy level of an electron is 1. And so he proposed the existence of these energy levels that surrounded the atom. And these would represent different inherent energies of the electron. So each of these orbits would have a different energy. So Bohr developed an equation associated with the energy levels, and it's shown here that the energy of an electron in one of these orbitals was equal to some constant divided by times 1 over n squared, where n is what we call the principal quantum number. And so, as you get to higher energy levels, the energy of the electron increases. Now that's added energy to the electron, with n of 1 being the lowest energy. At the lowest energy level, n is equal to 1, we have our largest, most negative energy. So another way of thinking about this is that the low point would be the most negative. In this case, it would be n is equal to 1. And then the next highest, n is equal to 2. And the next highest, n is equal to 3. And these get closer and closer together. And these are slowly going up in energy. There is no n is equal to 0. That doesn't. So this would represent the energy, and eventually at n is equal to infinity, the electron would have enough energy that is no longer associated with the nucleus. And so any energy difference between these, the quantum leap from one to the other, could be represented by the difference in energy between these, the change in energy, delta E. And so we can use this 2-point model that Bohr developed to predict the energy change. This is exactly what he did. He predicted energies associated with each of the transitions. N is equal to 2 going to n is equal to 3, n is equal to 4 going to n equal to 5, for the hydrogen atom. And then someone went out and found them. Again, these energy changes correspond to light frequencies. So we can relate this change in energy to h nu, a frequency. And so if we know the energy level 1 to 2, we can predict the frequency and then go look for absorbances or emissions in that frequency. And that's exactly what people did. It sort of highlighted the quantization of energy.